We are going to skip ahead a couple sections and we will come back to sections 2, 3, and 4 most likely. But we're going to kind of stick with working with polynomials. And a lot of what we did in the last section with the practice of division is going to come in handy here. So we're going to start thinking about remainders. And we have this theorem, okay, so we're going to get mathematically technical here. And we have this theorem that says let f be a polynomial function if that function is divided by x minus some number, then the remainder is f of c. All right, so let's think about that. What that means is if we divide a polynomial by a linear binomial, that's the same thing as x minus some number, and we tend to call that number c. If we divide by x minus c, we can find the remainder, but we can also find the remainder if we just plug c into the function. All right, so we're going to use the remainder theorem to look at this polynomial, and we're going to divide by x minus 3. Now, first we're going to just plug in the 0. All right, so the 0 here is 3, because if I set this equal to 0, I get 3. And if I plug in f of 3 into the polynomial function, I'm going to have 3 to the third power minus 4 times 3 squared minus 5. And if I simplify all this, 3 to the third power is 27. 3 squared is 9 times 4 is 36. And then minus 5. 27 minus 36 is negative 9, minus 5 is negative 114. Negative 14. So let's look at what we were just doing with synthetic division. Now my 0 we already said was 3. If I take 3 and I use that as my number that I'm going to use in synthetic division, my coefficients here, I have a third power, second power, I'm missing a first power, so I'm going to have to hold the place with a 0 and a minus 5. So I have 1, negative 4, 0, negative 5. And if I bring down a 1, 1 times 3 is 3, and when I add down I get negative 14. 3 times, I'm sorry, I get negative 1. Ugh. 3 times negative 1 is negative 3. Add down, I get negative 3. 3 times negative 3 is negative 9. Add down, I get negative 14. So there's two ways that we can find out what the remainder is. All right, so let's do another one. This time, my 0 is negative 2. So if I need to know what the remainder is, I can plug in negative 2 into the same function. So I have negative 2 to the third power minus 4 times negative 2 squared minus 5. Negative 2 to the third power is negative 8. I'm going to square first, so that's positive 4 times negative 4, that's minus 16, and then minus 5. So if I subtract or add these all up, negative 8 minus 16 is negative 24, minus 5 is negative 29. All right, same thing with synthetic division. My 0 is negative 2. I'm using the same function, so I can use the same numbers as my coefficients, or I hope I do. 1, negative 4, 0, negative 5. Bring down the 1. Negative 2 times 1 is negative 2. That would give me negative 4 minus 2 is negative 6. Multiply, I get 12. Add down, I get 12. Here I get negative 24. Add down, I get negative 29. All right, just showing that there's two ways to do division and find out what the remainder is. Now, what we ended up looking at in synthetic division is we were using division to find out if we get remainder 0, because then we would find a factor of the polynomial. So basically there's another theorem here that says if you plug in c into the function and the remainder is 0, that means that x minus c is a factor and c is a 0. All right, so if I get a remainder 0, I have a factor and a 0. Okay? So that's why it's important not necessarily to know what these numbers are, but to know what the remainder is going to be. So then it says to use the factor theorem to determine whether the function x minus 1 is a factor. All right, so I'm going to have the 0 be negative 1, or 0 is positive 1, and I want to know if it is a factor. So I can take 1 and plug it into my function. So if I find f of 1, I'm plugging in 1, so I have 2 times 1 cubed minus 1 squared plus 2 times 1 minus 3. So 1 cubed is 1 times 2 is 2 minus 1 plus 2 and then minus 3. 2 minus 1 is 1, plus 2 is 3, minus 3 is 0. So because I get equal a remainder of 0, that means that x minus 1 is a factor. All right, let's see if x plus 3 is a factor. So if I take my 0, which is negative 3, and find f of negative 3, I have 2 times negative 3 to the third power minus negative 3 squared plus 2 times negative 3 minus 3. So I have negative 3 to the third power is negative 27, and then times 2 would be negative 54. Negative 3 squared is positive 9, so I'm going to subtract 9. Plus 2 times negative 3 is negative 6, then minus 3. Now all I'm asked to do is to find whether this is a factor. So I just need to find out what the remainder here is. And I know that it's not going to equal 0 because I start with negative 54 and I keep subtracting, so I keep getting a bigger negative. So this does not equal 0. So x plus 3 is not a factor. So when we're looking at polynomials, it is helpful to know how many possible zeros we can have. And it's a very simple rule that the degree tells us the maximum number of zeros I can have. So if I have a third degree, I have 3 possible zeros. Or maybe I could say instead of 3 possible zeros, I have at most 3 zeros. Okay, I could have 3 zeros, I could have 2 zeros, I could have 1 zero, but I can't have 5 because that's more than the degree. If I have a 4th degree polynomial, then the most number of zeros I can have is 4. 4 at most. Or maybe I should say at most 4 zeros. All right, so if I have a really large polynomial, and let's say I have, if I even just look at this example down here, I have something to the 7th power, and we're going to factor these. So I know that I could have at most 7 factors, or I can have up to 7 factors. So it is going to be helpful, especially if we have a very big degree, that we have some tricks to help us narrow down what the possibilities for our zeros are. All right, so we don't want to just go in there blind with trial and error, because there are some things that can help us determine where to start. The first one is called the rule of signs, and this is made or determined or made up or invented by a French mathematician named René Descartes, and he studied polynomials, and he found a pattern in terms of polynomials and the sign changes within a polynomial. So if I look at how many sign changes there are, so by sign changes, this first term is negative, this second term is positive. So from negative to positive, I have a sign change. Then from positive to the next term is positive, there's no sign change here. But then I have a positive to a negative, so here's another sign change, and then a negative to a negative. So this tells me here, if I look at this, I notice I have 2 sign changes. Okay, so that is for f of x. Now, when we're looking for factors or the zeros eventually, some of our zeros are going to be positive and some of our zeros are going to be negative. And if I look at the sign changes when x is positive, this tells me I can have 2 sign changes or any even number less than 2. So that means if I think of the even numbers less than 2, I can have 2 or 0 positive roots. Because if I look up here with my degree is 7, so I can have up to 7 factors in here, and when I solve those factors and get the zeros, 2 of them could be positive zeros, and then there are others that could be negative. So to determine if we can have, or how many negative roots we have, I'm going to plug negative x in for x. So when I plug in a negative, so I'm just going to look here, I have negative x to the 7th power. So a negative to the 7th power is still negative. And multiplied by -3, I end up with a positive 3x to the 7th. Now I'm going to go through and do this with every term. I'm going to plug negative x in for x. So maybe I'll do this down here. So I had -3 and then negative x to the 7th power. So this is negative times a negative So this term now is positive. So then I have plus 4, and x is now negative x to the 4th power. So 4 to the 4th, or x, or I should say a negative to the 4th power, is a positive number. So a positive times a positive is going to be a positive 4x to the 4th. And then I have plus 3x squared. So plus 3, and x is now negative x squared. If you square a negative, that's positive, times a positive is a positive. So that's plus 3x squared. Then I take a negative x and put it in for an x here. So I have minus 2 times negative x. Well, now I have minus and a minus, so this would be a plus 2x, and then a minus 1. So after I substitute for negative x, I'm again going to look at the sign changes. So from positive to positive, that doesn't change. Positive to positive, it doesn't change. Positive to positive, it doesn't change. But positive to negative, this is where my sign changes, and it only changes one time. So I have one sign change, and that means I'm going to have one negative root. And that means these roots are going to be real numbers. Okay? So we're going to do some more practice with this. How many sign changes are in this polynomial for x and for negative x? So if it's just x, I can just go through here and look. So I start with positive and I go to negative. So there's 1. Negative to positive is another 1. Positive to positive is not a change. Positive to negative, and negative to positive. So in this case, if I count, there are 4 sign changes. Okay, so that means, and this is a positive x, so my positive roots, numbers that are positive, could be 4, or any even number less than that. So it can be 4, or 2, or 0. Okay. And that will click in later on why that works. Now looking for our negative roots. How many negative roots can we have? It's dependent on how many sign changes there are for negative x. So if I plug in negative x to the 5th power, that becomes negative x to the 5th power. So just looking up here, negative x to the 4th power is a positive x, but I have a minus here, so I'm going to minus x to the 4th power. Negative x to the 3rd power is negative x to the 3rd power times a positive, so a negative times a positive is now a negative 3 times x to the 3rd. Negative x squared is positive x times positive 9, so that'd be plus 9 x squared. Negative x in for x. A negative x times a negative is a plus x, and then plus 5. So hopefully you are recognizing that if I have an even exponent, the sign stays the same. If I have an odd exponent, I'm going to change the sign. All right, so x to the 5th, we changed it from positive to negative. X to the 4th, it stayed the same. X to the 3rd power, that's an odd exponent, we changed the sign. So any odd exponent changes the sign out in front. So now we're going to count them up. So I'm going from negative to negative to negative, no change here. Now negative to positive is 1, and positive to positive to positive, there are no more sign changes. So for my negative roots, there are only 1. Okay. All right, so this tells us how many factors or roots that we are going to be looking for when we start to factor. So the next the next theorem tells us, well, that still kind of is explaining up here, but the next example with our roots is going to help us determine what the numbers inside the factors are. So remember, our factor is going to be x minus some number. And those numbers, we don't just guess at random. There is a method to help us find out which ones we can try for trial and error. And it has to do with the coefficients of the first and the last term. Okay, so if I look up here, I could have 7 real number roots, or 7 real zeros at most. So I could have 7 or 6 or 5 or 1, but I can't have more than 7. So if I look at, again, this, I was getting ahead of myself. We're still doing the same thing up here. So if I'm just determining how many roots I can have, again, if I find f of x, I was getting ahead of myself here, but I can have up to 7 roots. I have some roots that are positive and some roots that are negative. So if I'm looking at positive x, I'm counting the sign changes. I'm starting here with positive to positive to positive. So here's a sign change, and here's a sign change, negative to positive. So here I have 2 sign changes, which means I can have 2 or 0 positive roots. Okay, so out of my 7 zeros, okay, 2 of them or none of them are going to be positive numbers. Now, the negative test is a little more difficult because, again, we need to plug in negative x. So let's think about our exponents being odd or even. So a 7th power of a negative is negative, so we change the sign. So I have negative 4x to the 7th. If I plug in negative x, it becomes positive, so that sign stays the same. For the 5th power, that's an odd exponent, so your sign's going to change, minus x to the 5th. Even exponent, your sign will stay the same, plus 2x to the 4th. Odd exponent, your sign will change, plus x to the 3rd. Even exponent, it stays the same, plus 9x squared. X to the 1st power is odd, so I change my sign to minus x, and then I have plus 1. So if we count our sign changes now, I have negative to positive, positive to negative, negative to positive, 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 positive to negative, negative to positive. So what this means now, if I count 1, 2, 3, 4, 5. So my negative roots could be 5, but then I'm going to go down multiples of 2. So it could be 5, or it can be 3, or it can be 1. But there's going to be at least one negative root. It could be 5, it could be 3, and I may not have any positive roots. All right. So getting into the next part, the next trick that's going to help us find what our roots are going to be in a big polynomial that we're going to have to factor. And this is called the rational root theorem. Okay, so we're talking about rational numbers. Okay, rational equals fractions, or in fraction form. All right, so this is kind of hard to understand theoretically, but what all this means is at the beginning of my terms, I have a first term and I have an ending term. This first term, I'm looking at the coefficient and I'm calling it Q, and this last term, the coefficient is P. And I'm going to take all of the factors of P and divide it by all of the factors of Q. Okay, so I'm going to factor them. So all P is the last term, term factors, and Q is first term factors. And we're going to make as many matches from them as we can. All right, so that probably made absolutely no sense. But here it is with real numbers. In this, my first term, which is P, it's Q, Q comes first, is 2. And my last term is 6, and that's going to be P. So now we want to find all of the possible combinations when we do P divided by Q. So P is 6, Q is 2, and if I factor all of these, the factors of 6 are 1, 2, 3, and 6. The factors of 2 are 1 and 2. Now I'm going to make as many rational numbers from these sets of numbers that I can. So that means if I start with 1, I have 1 over 1, which is 1. I have 1 over 2, which is 1/2. Now I can go to the next one. I have 2 over 1, which is 2. And 2 over 2, which I already have, is 1. Then I have 3 over 1, which is 3, and 3 over 2 is 3/2. And then I go to 6. 6 over 1 is 6, and 6 over 2 is 3. So these are the numbers, the positive and negative values of those, that I can use to help find what the polynomial factors or the zeros are going to be. These are possible zeros. All right, so let's do some more. Rational x-intercepts. These are the same thing as zeros. All right, so our first term is Q, so Q is 1. Our last term is P, P is 12. So I'm going to do P over Q. So I need the factors of 12 and the factors of 1. Factors of 12, and I got to make sure I get them all. So I like to do factor pairs. So 1 times 12, 2 times 6, 3 times 4, and now I have them all. And the factors of the Q number, 1, is 1. So the possible roots that I have are positive and negative values. 1 divided by 1 is 1. 2 over 1 is 2. 3 over 1 is 3. 4 over 1 is 4. Then 6 and 12. All right. So 1, 2, 3, 4, 5, 6. There's 6 numbers here that are possible zeros, but I have positive and negative. So if I were going to do some trial and error to determine which are zeros, there's 12 possible numbers that I can choose from out of this list. All right, here's another one. Find all possible rational x-intercepts, or zeros, of this polynomial. All right, so this is our Q, this is our P. So I have P is 5 and Q is 2. So the factors, okay, so I want to factor these. Factors of 5 are 1 and 5. Factors of 2 are 1 and 2. So I'm going to make as many rational numbers as I can. So I'm going to have positive and negative values. I'll have 1 over 1 and 1 over 2. 5 over 1 and 5 over 2. Okay, so these are the only numbers that could possibly be one of those zeros. All right, so there's one more, and this one has a lot. So when you have lots of numbers, or numbers that have lots of factors at the beginning and at the end, there are a lot of things that we'll possibly have to try to find out what those roots are. So my first number is 6, that goes on the bottom. My last number is P, that goes on the top. And the signs here don't really matter because at the end we're going to use positive and negative values anyway. So the factors of 30, 1 and 30, 2 and 10, or 2 and 15, 3 and 10, and 4 doesn't go into 30, but 5 does 6 times. So all of these numbers are factors of 30. The factors of 6 are 1, 2, 3, and 6. So now if I make a list of all of these combinations of rational numbers, remember every top number goes with every bottom number, and they can be positive or negative values. So do it in some kind of systemic way. So I'm going to just start with each number and put it with each number on the bottom. So I could have 1 over 1, I could have 1 over 2, I could have 1 over 3, I could have 1 over 4, or 1 over 6, sorry. 1 over 1, 2, 3, and 6. Then I can have 2 over 1, which is 2. 2 over 2 is 1. 2 over 3, I don't have here. And 2 over 6 is 1/3, which is already here. Okay, so sometimes they appear more than once, but we only have to write them one time. Then I'll go to 3. 3 over 1 is 3. 3 over 2, I don't have that one yet. 3 over 3 is 1. 3 over 6 is 1/2. Then I go to 5 over 1, which is 5. 5 over 2. 5 over 3. and 5 over 6. Then I have 6 over 1 is 6, 6 over 2 is 3, 6 over 3 is 2, and 6 over 6 is 1. Then I have 10 over 1. I'm going to start another row here. 10 over 1, 10 over 2 is 5, it's already there. 10 over 3, 10 over 6. Now 10 over 6 is the same thing if I reduce it as 5/3, which is already here. Then I have 15 over 1, 15 over 2, 15 over 3 is 5, 15 over 6 is, if I divide by 3, is 3 over 2, which is already there. And then 30 over 1. 30 over 2 is 15, 30 over 3 is 10, and 30 over 6 is 5. So there are several combinations that I could have here. I'm going to have at most 4 factors. And if I look at this, I'm putting some things together, I would have 4 factors. And if I look at sign changes, this is positive to negative to positive. There's, oops, was that positive? Yes. That was a positive 6, sorry. I had a pen mark there, I thought it was negative. So positive to negative is 1, 2, 3. So I could have 3 or 1 positive factors, or zeros. And then if I look at, if I put f of negative x, I'm going to have negative x to the 4th power. The sign stays the same, so I'm just going to write the signs here. That's all I need. This is positive. A negative exponent will change the sign. That would be positive. An even exponent keeps the sign the same. An odd exponent changes the sign. So positive, and then this is positive. 1, 2, 3. This is positive. And 0 power, nothing changes. So this tells me that there is going to be 1 negative 0. So I could have 1 negative and 3 positive factors, and that would give me 4 total. Okay, they don't always have to add up, but they most likely will. All right. I think I'm going to stop here, and we're going to put all of this together in the next lesson.